My name is Luke Shui. I'm a junior.
My name is Melissa Lee. I'm a senior.
My name is Sophia Rong. I'm a junior.
My name is Andrew Zing, and I'm also a junior.
And we are presenting our solution to this year's M3 challenge, A Tale of Two Crises. In part one of this year's challenge, we were tasked with predicting the housing market in our two chosen regions of Seattle, Washington, and Albuquerque, New Mexico for the next 10, 20, and 50 years. Because we're examining the housing market in the context of increasing homelessness, we chose to examine the quantity of vacant or available housing, as these are the homes available for purchase or occupancy, making them most relevant for the problem. We defined the various ways a home could enter or exit the state. New homes being constructed or old homes being put up for sale would enter the state of vacancy, while the only way a home could exit the state was by being purchased. We then, as the M3 challenge itself notes, construction of new housing is difficult and time-consuming. As such, for the purposes of this problem, we assumed that the rate of construction of new homes will remain constant due to the difficulties associated with ramping up production. We then obtained data via Zillow for the past 6 years on sales and listings within both our regions, and noting the extreme seasonal trends shown by our data, we decided to use a seasonal autoregressive integrated moving average, or SARIMA model, to represent this data.
The SARIMA model has a total of 7 parameters, and because it is a time series, it uses previous data to predict values in the future. The number of prior values used is specified with the parameter p. To calculate p, we took a look at the partial autocorrelation function. Now, partial autocorrelation measures the direct correlation between two elements separated by a time lag by removing the effects due to other events within that time lag. It mathematically is the correlation between the residuals of those two lag time series events. We use partial autocorrelation to calculate p because it has the ability to figure out which one of those previous events has the highest correlation with the current data value. Looking at our partial autocorrelation graph, we see that after the first month of lag, the autocorrelation decreases significantly, which means that we only have to use the previous month's data to predict values in the future. Our second model parameter is D, which specifies the number of finite differences required. One key assumption that SARIMA makes is that the time series has to be stationary. In other words, the mean of the data set has to be roughly constant throughout the time series. In order to make it stationary, we require the usage of finite differences. Below shown is a general model of the autoregressive model, which is the first part of the ARIMA model. The augmented Dickey-Fuller test tests whether or not alpha in this equation is 1, which would signify that we would have to take a finite difference as it is not stationary. After applying the test to Seattle and Albuquerque, we found that neither required any finite differences and both were actually stationary. Our third parameter is Q, which represents the number of white noise error terms used to predict the current value. And to do this, we looked at the autocorrelation function. Now, the autocorrelation measures simply the correlation between the value and the lagged version of itself. And because this correlation includes the white noise error terms, we decided to use the autocorrelation to calculate Q. Similarly, with the partial autocorrelation, the autocorrelation decreases significantly after the first month of lag, which means we only have to use the previous month's white noise error term to predict values in the future. This constitutes the moving average portion of our ARIMA model. The next 4 parameters distinguish the SARIMA from the ARIMA model, as these parts incorporate seasonality. Big P, big D, and big Q represent the seasonal equivalents of P, D, and Q. And after analyzing our data set, we found that big P equals 4, big D equals 1, and big Q equals 1 produces the best fit, as this produces a graph that isn't too spiky, isn't too round, and also isn't too repetitive. Our final parameter is S, which represents the length of the seasonal cycle. Housing market analysis has showed that typically housing markets involve a seasonality of around 12 months. And this is shown in our partial autocorrelation and our autocorrelation graphs, as we see a very significant correlation in our 12th month lag. Once we determined all of these parameters, we still had to pre-process the data, as SARIMA makes another assumption that the variance is held roughly constant. In other words, the variance is stationary. To make the variance stationary, we use the Buchholz transformation, and specifically the Buchholz transformation with lambda equals 0, as this stabilized the variance the most out of all the other lambda functions. These are our 2 graphs. The first one is the Seattle sales. The second one is the new listings in Seattle. The orange represents the given data set, as in Zillow, and the blue represents the predicted data values. As we can see, the sales slightly outpaced the new listings, but this is offset by the constant rate of production.
following two tables show our model's results for both Seattle and Albuquerque. In Albuquerque, we saw a 600% increase in the supply of vacant housing over the next 50 years, with a similarly large 500% increase in Seattle. Compared to the homeless populations in both of these regions, which number approximately 1,500 and 10,000 respectively, it is clear that the root cause of homelessness is not due to a lack of physical housing supply, but the increasing unaffordability of existing homes. Our REMA models allow us to capture both short-term seasonal variations in our time series data, while also capturing longer-term trends. Additionally, through the use of an augmented Dickey-Fuller test, as well as autocorrelation, we are able to objectively determine our model's parameters, providing a more accurate prediction. However, REMA models in general rely heavily on past data, which makes them less reliable to predict extremely long-term predictions. But in general, this is a problem with attempting to predict far into the future, as it's rather naive to assume the current status quo will remain constant over the next 50 years.
Problem 2 tasks us with predicting the homeless population in Seattle and Albuquerque within the next 10, 20, and 50 years. To quantify homelessness, we must first define it. For the purpose of our model, we define homelessness as when an individual's income falls below the cost of their basic necessities. Therefore, they will be forced to give up some sort of expenditure in which we assume will be their housing. Furthermore, we define chronic homelessness as individuals who stay homeless for extended periods of time, whether due to financial circumstances or by choice. To quantify homelessness, we employ a Monte Carlo simulation where we observe an individual's income versus expenditures across their lifetime. We simulated a number of individuals proportional to both Seattle and Albuquerque's populations and used distributions that are different for their income and expenditures. As our model is only a prediction of the real world, we have to make a number of assumptions. First, to account for inflationary pressures, we assume that real incomes will stay fixed over one's lifetimes. This means that we do not account for job promotions or job changes, as these are more likely to increase an individual's income and therefore make them less likely to fall into homelessness. Furthermore, this makes our model more likely to be an overprediction of homelessness. Second, on average, we assume that people will become independent at age 25 and retire at age 65. These numbers are consistent with the Bureau of Labor Statistics. Third, as we are predicting in the far future, we have no way of predicting any economic shifts. So therefore, we assume that distributions of price and income will remain the same relative to each other in the foreseeable future. Fourth, we assume that the government will not intervene to solve the homelessness crisis, as it is difficult for us to account for government policy. And finally, according to the National Alliance to End Homelessness, approximately 22% of homeless people have patterns of chronic homelessness, and the remaining 78% have a median time to rehouse of 241 days, which is 2/3 of a year. We model an individual's income and expenditures on a yearly basis. So when the model begins, we assign each individual with an income taken from a normal distribution, respective of Seattle and Albuquerque. But for a given year, there are 3 possibilities as to the income they actually receive. First, if they are employed, then we simply just add their income to their total amount of money. After subtracting the cost of their basic expenditures, then what is remaining, we allow 2/3 to carry over into the next year as their savings. Second, at any given year, we allow a 1% chance for an individual to get laid off. When this occurs, we allow them to have unemployment benefits for up to 12 weeks. Finally, if they exceed these 12 weeks, then they will be considered unemployed and therefore will receive no income. We are only modeling the cost of basic expenditures, as even for individuals with high income, they will be able to, if they receive sudden price shocks, such as possibly losing their job or having medical emergencies, then they can simply reduce their other unnecessary expenditures. And therefore, the only costs that we necessarily need to consider are the costs of food, healthcare, housing, transportation, and clothing, which we have deemed to be the necessary expenditures that anyone must spend their money on.
To calculate the average expenses, we multiplied the national average by a conversion ratio for each necessity, and we only considered the bottom 20% of the population, as this is the group most representative of those likely to become homeless. And this gives us the cost of living for each city, which gives us a standard to base our expenditure off of. Due to the particularly long time frame, we wanted to be able to accurately represent the changing population. So we decided to simulate each age group separately as they spend different amounts of time in the workforce. The number of years spent working is important because this determines the period of time for which they are vulnerable to homelessness, the time of independence between age 25 and 65. Shown above is our table for the 50-year time window, but we have similar ones for the 10 and 20-year distributions. From our Monte Carlo simulations, these are the projected increases in the homeless populations for the next 10, 20, and 50 years. And in order to validate our results, we calculated the real change in Seattle's homeless population over 10 years with different starting days, and the number varied from 2,500 to 4,500. Our prediction of 3,800 falls well within this range, so this validates the accuracy of our model. Our 10-year number for Albuquerque was similarly accurate, though because the city government has been slowing the growth of homelessness through intervention programs, our 20 and 50-year predictions will likely be over predictions if they continue to do this. Our model elucidates the importance of each factor since the cost is directly proportional to the burden felt by the individual. Additionally, because we use random selection in a normal distribution, this adds variability that is reflective of real-world situations. And we can also easily modify parameters or assumptions, which allows us to determine the sensitivity of our model with respect to different factors. However, this also means that we cannot capture the intricacies of real situations since we only have a limited set of variables. And as always, long-term prediction is always unreliable, especially over 50 years.
So the final section of this year's challenge urged us to develop a model that could help local governments determine a long-term plan to address homelessness. So going back to the first section of our report, we determined that recent increases in homelessness have been due to a lack of affordability in current housing options, rather than a shortage in housing supply itself. So, drawing inspiration from existing federal government subsidies, we decided that a potential solution was for local governments to offer a form of subsidy of their own, which would bring current housing to a more affordable price. Utilizing the Monte Carlo simulation in Model 2, we were able to implement these subsidies by decreasing the price of housing by varying subsidy amounts. So the results of certain subsidies are shown in the table here, with significant percentage reductions in Seattle's homeless population over the next 50 years. However, it is important to note that the efficiency of these subsidies tapers off from 20 to 50 years, which may indicate that the subsidy has reached its maximum efficacy or is now in a steady state. Still, it is clear from our model that these subsidies have great successfulness at decreasing the number of people experiencing homelessness, and we believe that this tool can be used to great effect by local governments in order to solve this crisis. Also, in the case of Seattle, we determined that the subsidy of value $2,500 may be the most worthwhile or cost-effective, with a 17% decrease in 50 years. However, this does depend on limitations such as the city's budget. So a strength of our model is that it is easily adjustable, as all we have to change are our input parameters, making it widely applicable to new cities. Additionally, we can account for further unforeseen circumstances, such as natural disasters, economic recessions, or increased migrant populations through changing our job loss factor in our Monte Carlo simulation, or by modifying additional variables as needed. However, we only examine homelessness from an economic perspective, which fails to account for some more personal intricacies, such as drug abuse or mental health issues that may affect increasing rates of chronic homelessness, especially in Seattle. And we also, with more time, we would like to have evaluated possible effectiveness of other incentives, such as food subsidies or tax credits, to determine the most effective combination of aid in order to combat homelessness. In summary, in Model 1, we were able to determine that although there is an excess in housing units, costly prices will continue to stop many from purchasing homes, with an estimated 500% and 600% increase in vacant homes in Seattle and Albuquerque over the next 50 years, respectively. And in Model 2, we were able to determine that without further government intervention, the homelessness crisis will only continue to worsen. And in Model 3, we decided that the most constructive solution for these problems is for local governments to offer a subsidy of their own. And this was shown to be a fairly cost-effective solution with a large percentage reduction in the number of people experiencing homelessness. As a whole, we believe that all three of our models are flexible enough to be generalized to further cities and can provide useful insights in order to alleviate the housing and homelessness crises. We would like to open the floor to any questions, and we would also like to thank our coach, Mr. Liu, and M3 and Jane Street for inviting us here.
Great, thank you.
Okay, good morning. Can you hear me?
Yeah.
Okay. So I have a question about part one of your model predicted a very huge increase in the housing supply for both cities. Your numbers were higher than most teams predicted. So my question is, was there an aspect of your model that led to such a high increase? And do you think this is realistic?
Well, it's obviously very hard to predict anything in the next 50 years. So there's a large variation in any sort of predictions. In our model, we noticed as we can see in the graphs here, the constant rate of production did overcome the deficit in sales and new listings, and that's what caused us to have a rather high change in the housing supply over the next 50 years.
I think one thing to also consider. I think one thing to also consider is the government permits, such as single-family zoning, single-house zoning. So, for example, if governments start to shift towards allowing multiple homes to be built on one plot, that would all create a way for much more housing to be available within these cities, and so that's potentially like something our model could predict.
Okay, thank you.
Again, a question about the Monte Carlo simulation. Can you go into a little more detail on how you estimated how people go from the unhoused to housed population and backwards?
So you mean like how someone goes from being homeless to like getting a job again? Okay, so essentially what we did is like, obviously our definition of homelessness is when an individual's income falls below the cost of their basic necessities. So this is basically the factor that we used. So we used basically the biggest thing that would affect someone going from being homeless to getting a home again is their income. So when we look at how we calculated yearly income, especially when we look at unemployment benefits, so essentially after an individual is like unemployed, they're more likely to become homeless. So this is where we were more likely to see numbers of homeless people. And so after they're unemployed for like a year, since we're modeling on a yearly basis, they have a fixed income, and basically we have like a probability of them like getting a job again, and then after they get a job, we compare their income versus their expenditures, and therefore if they fall below like the basic necessities, then they'll fall back into homelessness.
A quick follow-up on that. So when you did your Monte Carlo simulation, how many simulations did you do to estimate your future results?
Yeah. So I probably shouldn't have done this, but I actually used like the exact population for Seattle and Albuquerque, so it took me a long time to run the simulations. So I used like around, I think it's 700,000 for Seattle and like 500,000 for Albuquerque.
Suzanne, do you have a question? Do you have one? I want to ask a follow-up for that second question. I think it's reasonable to choose the population seed as the number of simulations. How would you know if you chose enough? Like if you've done 10,000 or 1 billion, how do you know if you got an accurate answer?
That's actually a really fair question. One thing, okay, so I'm actually not exactly sure how you would quantify it. I think it would be if your results are like necessarily too close to, like if you're overfitting your model, if you notice that like the data that you're getting is like very, very similar to the data that you expect. One thing I would be worried about is to not go maybe below like 10%. Like how much? Yeah, like as long as we have enough for a normal distribution to appear, which is
Probably 10,000.
yeah around 10,000.
And also, we had a very limited time frame, and also computation resources were at a premium, so we couldn't simulate a whole lot of times.
Any last questions? Okay, thank you.